All right, can you see my screen?
Yes, perfect. So the next speaker is William Kretschmer. We'll talk about symmetries, graph properties, and quantum speedups.
Great, thank you for the introduction. And this is based on joint work with this wonderful group of 5 co-authors, Shalev Ben David, Andrew Childs, András Gilyén, Supartha and Daochen Wang. And I'll start by just going through the kind of background and motivation for this work. So like a lot of other work in quantum complexity, the goal of this work is sort of to understand, to better understand what are quantum algorithms good for. And you know, by far the most famous example, if we're interested in like super-polynomial or even exponential quantum speedups, the best known example are, of course, factoring a discrete logarithm, which we have a polynomial time quantum algorithm that beats all of the best classical algorithms, which take exponential time in general. But, you know, of course, even these are only conjectured, right? We don't know how to actually prove that factoring requires exponential time, much less do we know how to prove p is not equal to np, let's say, right? So, you know, how can we give any evidence at all that quantum algorithms are actually able to do something that classical algorithms can't? Is there any, you know, is there any provable sense in which quantum algorithms can actually do something classical algorithms can't? Well, if the answers to that question were no, I would not be giving this talk. Of course, the most common way we answer these sorts of questions is by looking at the query complexity model. And in the query complexity model, there's always 2 objects. There's a function f, which is known, and an input x to f, which is unknown. And your goal is just to evaluate f on x. So f takes in n inputs. Here there's some alphabet sigma. You can think of this as just being a binary alphabet. And of course, the way you access x is that you have access to some black box, which on input I just returns the ith bit of x. And your goal is to evaluate f on x using as few queries to this black box as possible. Otherwise, all of the computation is free. And of course, in the quantum model, you don't just get to make queries to f, but more generally, you get to make queries in superposition. And formally, of course, the way that's defined, you get access to some unitary that an input register, a target register, and a workspace register, it just XORs the ith bit of x into the target register. And so in this model, there's sort of 2 relevant complexity measures of interest. There's Q of f, the quantum query complexity, and R of f, which is the classical randomized query complexity of f. And we're just interested in how many queries you need to compute it to bounded error, so say with probability 2/3 of correctness. And as I said, basically what we're interested in is when can Q of f be, say, exponentially or at least super polynomially smaller than R of f. Now, why do we study query complexity? Well, I think there's sort of 2 main reasons, right? One is something I kind of alluded to in the first slide, which is that unlike a lot of other things in query complexity, we can actually prove unconditional separations. The other reason is that in practice, it also just captures most quantum algorithms, maybe even almost all quantum algorithms. And just to give an example, going back to, you know, period finding, in some sense, Shor's algorithm is not really a factoring algorithm. What it really is it's a quantum query algorithm for a problem called period finding, which can be solved in a constant number of quantum queries, whereas a very large number of queries are needed for any classical randomized algorithm. And then Shor's algorithm is just this query algorithm along with the observation that you can reduce factoring to period finding. But like I said, the motivation for this work is basically to understand what sorts of problems can we expect these like really large query speedups where the quantum query complexity is much, much smaller than the randomized query complexity. And some of the foundational results in this direction actually are negative results. The first one I'll mention, this was, you know, one of the most important early results in quantum query complexity is that for all total Boolean functions, there is at most a polynomial separation between randomized and quantum query complexity. This used to be a 6th power relationship, but of course this was recently improved this year by Aaronson et al., presented earlier at QIP to a 4th power separation. And so this shows that you need, if you want some sort of exponential speed up, you need a partial function. And another result in this direction by Chailloux in 18, again, kind of improving an exponent on an earlier work, shows that for permutation invariant functions, there also cannot be any speedup. And here, this is permutation invariant just means a function that takes in n inputs such that you can rearrange the input arbitrarily, and this does not change the value of the function. And again, this is over like an arbitrary alphabet, and it also includes partial functions. And I just want to emphasize that this is an extremely broad class of functions already, for which there could be no quantum query speedups beyond this 3rd power. This includes things, obviously trivial things like majority, parity, or let's say, but it also includes highly non-trivial things like, let's say, the collision problem or element distinctness, problems for which it was actually highly non-trivial to obtain tight quantum query lower bounds. And in some cases, when it's not obvious at all whether there could be an exponential speedup. And this, finally, with all of this, this sort of brings us closer to what we study in this work, which is what is the role of symmetry in these quantum query complexity speedups? And this last theorem due to Chailloux kind of gives, again, one result in this direction, which shows that if a function is completely symmetric, there cannot be a speedup. But what about other kinds of symmetry? And one of the motivating examples in this direction is graph symmetry. So here I've drawn 2 graphs, but of course they're actually really the same graph, just drawn differently, right? I've just permuted some of the vertices. And the relevant, I guess, class of symmetric functions to look at are, of course, graph properties. So what do I mean by a graph property? Well, a graph property is just anything that is, invariant under the isomorphism type of the graph, or another way of saying it, it's invariant under relabeling of the vertices. So this includes things like bipartiteness. Is the graph connected? Is the graph a tree? This would not include things like, say, ST connectivity. Is vertex S connected to vertex T? Of course, because this depends on the labels of vertices S and T. But it's interesting to note that already this is a much smaller group of permutations compared to full permutation symmetry. So for a graph with n vertices, right, there's like n factorial ways you can permute the vertices, but that's much, much less than all the different ways you can permute the edges, which is like n choose 2 factorial. So, and it was actually explicitly raised by Montanaro and de Wolf as an open problem in 2013, I believe, whether or not there can be a super polynomial quantum query complexity speedup for any graph property. Now, one thing that's important to note is that there's always 2 natural ways to represent graphs in the query complexity model. One is the adjacency matrix model, where you basically query a pair of vertices and ask, is there an edge between them? Or I guess more generally, you can ask, what is the label of the edge between them? Which in this case would just be like 0 or 1, say if there's either no edge or an edge present. But of course, there's also the adjacency list model, where instead you just query a single vertex and you get back the list of, and there between these 2 models. So, which actually opens the question of Montanaro and de Wolf, randomized and quantum query complexity. And this follows as a corollary of a more general result that for hypergraph symmetries, there's at most a uniform, meaning all hyperedges involve exactly k vertices, there's at most a 3K power speedup between randomized and quantum query complexity. So again, this resolves this question in the adjacency matrix model. This also, in a way, raises another question on its own, though, which is, what can we say about other kinds of symmetries, right? So more generally, let's say you have some function on n inputs, you can look at an arbitrary permutation group. So if you have some permutation group G, you can say f is symmetric under G if you can permute the input of f according to any permutation in G, and it does not change the value of f. So graph properties were one special case, but what about other permutation groups? Well, what we show in this work is essentially that actually graph properties and more generally hypergraph symmetries are essentially the only interesting case, in the sense that that's the only case where the permutation groups are inconsistent with super-polynomial quantum speedups, in the sense that any permutation group that is not constructed out of hypergraph symmetries, you can always find a large quantum query speedup. And this statement here is kind of deliberately informal because the actual statement of our result is a little bit technical. In case there's any group theorists in the audience who are curious, this is what it is, but I'm not actually going to really explain this in much detail. But formally, we prove a dichotomy theorem for what are called primitive permutation groups. And this dichotomy depends on this quantity called B of G, which turns out to be the minimal base size. And this basically says that small primitive groups are consistent with large speedups, and large primitive groups are not consistent with large speedups. Additionally, we show, or rather it kind of follows as a result of the classification of finite simple groups, that actually all of these groups in case one essentially involve hypergraph symmetry. And so that's sort of the slightly more formal explanation of this result. And finally, we have one more result. So going back to graph properties, we have a result actually in the other model, in the adjacency list model, where we show that in direct contrast to the adjacency matrix model, there actually is a graph property with an exponential separation between the quantum and classical query complexity, again, classical randomized query complexity. And in fact, we show something even more general. We show there's actually a speedup like this for what's called property testing. And in property testing, your task is you're given that there's some graph property, and your task is to distinguish whether the graph has this property or whether it is far from having this property, which means that you would need to change an epsilon fraction of the edges in order for the graph to have this property, where epsilon is some constant. So that's basically all of our results. Are there any questions so far? Because I guess if not, I'll just move on to saying a little bit about how we prove these results. And starting with the no-go theorem for speedups in the adjacency matrix model. So our proof actually builds on the proof due to Chailloux for the case of fully symmetric functions. So Chailloux showed that this, at most, cubic separation between randomized and quantum query complexity for permutation invariant functions basically follows as a corollary of this theorem due to Gendre, who shows that, well, basically consider the following two distributions over strings of length n. And one of them, it's a random permutation, meaning you have a list of n numbers and each one appears exactly once. And the other, it's again a list of n numbers, but the range of this string has size at most r, where r is something smaller than n. What Gendre shows is that if you make queries to these, either pi or alpha, then in terms of r, you need a lot of quantum queries, specifically r to the 1/3, to be able to distinguish these two. I'm not really going to say much more about this. It's I mean, it is important why it is this particular problem, but I guess all I want to comment on is that it's sort of remarkable how this Chailloux's proof works, because what it shows it shows this incredibly general result, right? For any permutation invariant function, there's at most the separation, and it proves it via a sort of reduction to a specific, a quantum query lower bound for a specific problem, this problem of distinguishing a permutation from a small range function. So yeah, I think that's just quite remarkable. So how does our proof build on this? Well, basically, all we do is we observe that here, this Sn, this full group of permutations over n inputs, can actually be replaced by basically any group. And as long as you can prove some analogous statement, essentially the same proof due to Chailloux still goes through. So essentially, and again, like the proof of this corollary is exactly the same as the proof of this thing on the previous slide. The only new ingredient that's needed is this theorem here showing that distinguishing a random small range function from a random graph or hypergraph permutation is hard. And the way we do this is essentially the first thing you would try if you had to prove this. We prove it by actually a reduction to the theorem on the previous slide. And essentially, the key observation here is that graph symmetries are an action of the symmetric group. It's just a different action of the symmetric group. And there's a very natural way to go between the ordinary action of the symmetric group and this graph action. And this basically is the reduction between these two problems. So that's essentially all I'm going to say about this. And I'm actually going to move on to our second result about characterizing, which permutation groups are consistent with quantum query speedups. So as I sort of hinted at earlier, this result uses the classification of finite simple groups, and there's this theorem due to Liebeck, which again is fairly technical, so I deliberately made this small because I don't want you to read it. What I do want you to read is this translation into English, which shows that essentially for any primitive permutation group, either in some sense, G contains the symmetries of some hypergraph, in which case we can actually prove via the results of the previous section that there are no speedups, or this quantity B of G, this minimal base size, is like really small. In fact, so small that we can just always construct a function that's symmetric under G with a large separation between randomized and quantum query complexity. And this is essentially all there is to the dichotomy theorem, because again, this is covered by the first part of the theorem, and here we just explicitly construct speedups. So that's essentially the only important idea here. There are some, there's some other ideas that go into this for the case of like non-primitive permutation groups, but again, I'm not really going to say more about that in this talk. So finally, that brings us to the last part of this talk, which is the speedup in the adjacency list model for property testing. And this is probably the most technical part of this work. So I'm going to sort of, all of the remaining slides are just going to be pictures, basically. But I'll be able to say a little bit about some of the important ideas. So the starting point for this work is the well-known quantum speedup for what's called the welded trees problem. And here you have a graph that looks like this, basically. You have some balanced binary tree on the left and another balanced binary tree on the right, and they're connected by a weld, as we call it, just a random bipartite graph in the middle, basically. And your task is, given the label of this, what I'll call the entrance vertex, this root vertex on the left, your task is to find the label of the exit vertex on the right. And it turns out that this is a highly non-trivial result, but using a quantum walk, one can actually solve this problem exponentially faster than any classical algorithm can solve this on a quantum computer. So why are we not done, right? This is some graph problem, there's an exponential speedup. Well, of course, the problem is that this is not invariant under relabeling of the vertices, right? Here, the task basically explicitly depends on the label of the entrance and the exit vertex. But we can still use this idea to construct a graph property that has the desired symmetry. in particular, you can use some gadgets. So what we call basically, you add another tree to the end of these graphs, what we call an antenna. And then it turns out that if you have a graph that looks like this, where there's a weld in the middle, as opposed to a graph that looks like this, where there's not a weld in the middle, and instead these things are sort of welded to themselves instead of welded to each other, then again, there sort of is some sort of quantum speed up in the sense that a quantum computer can efficiently distinguish these two graphs, but a classical computer cannot, or at least cannot do so efficiently. But this is still not a property testing problem because while it can distinguish this from this, it's not clear whether you can distinguish this graph from anything that is epsilon far from this graph. And this is where we need yet more gadgets, basically. So the idea here is you, by sort of a series of complicated gadgets, you can add some structures that allow a quantum algorithm to efficiently test this weld structure in the middle, whereas a classical algorithm essentially cannot distinguish these from random. And again, this is pretty technical, but I will mention for people who know a little bit about quantum query complexity, this actually has a very similar flavor to cheat sheets, which are another technique for proving query complexity separations, because again, there's sort of some structure here that allows the quantum algorithm to efficiently verify that the graph is close to having this property. And so I guess now maybe it's good to mention, this is very, of course, artificial graph property, right? It's but nevertheless, it shows an existence. There's some graph property with an exponential quantum speedup, and so it leaves open the hope that maybe for something more reasonable, there actually could be interesting quantum algorithmic improvements. How am I doing on time?
You still have 2 or 3 minutes.
Okay. Let's see if there's anything else I can talk about. I mean, well, also, are there any questions so far?
There are a few questions.
Okay.
But we can wait a little bit after the end of the talk.
Yeah, okay. I guess I could also talk a little bit more about some of the other open problems. I actually originally had a slide, but I didn't think I would have any extra time. So yeah, one is just to give, are there other examples of graph properties that, of like natural graph properties with quantum speedups? Are there, for this dichotomy result for permutation groups? Well, in some sense, right, it's actually only a dichotomy result for primitive permutation groups. And there's actually some holes in the classification for more general groups. So another question is to sort of fill in some of those holes. And I guess finally, there's also just the natural question of whether these theorems are tight. So basically, what's the largest possible separation between randomized and quantum query complexity for graph properties in the adjacency matrix model? We know it's at most 6, but I think maybe the largest separation might even just be like Grover's algorithm, so like a power 2 separation. So this is just one interesting open problem that's left open here. And maybe with that, I'll end and take questions.
Okay, thank you, William. So we received a few questions on the slide. So one question that has been partially answered is, how do you model the adjacency list property in quantum algorithms?
Good. Okay, so for the purposes of our result, it sort of doesn't matter because in our result, all of the graphs have constant degree. Okay. So basically, you can just, you can sort of just have like a single symbol that just gives you the entire set of adjacent vertices. But yeah, I guess more generally, if you had like, a linear number of vertices or something, or some polynomial number, you would need some more complicated structure. But for us, it sort of doesn't matter.
Okay, because yeah, okay, it's constant degree, right? Okay, and another question, a little bit technical maybe, it's about what is the definition of the base of a group, so BG. And
Okay.
is it the same as the generators, maybe the number of generators?
Let's see if I can explain this. Okay, so the intuitive, well, okay, yeah. Actually, it has a nice intuitive definition for query complexity people. It's basically, what's the fewest number of queries you need to identify a permutation in that group? Mm-hmm. So to give some examples, so for the symmetric group, it's n-1, because you can query n-1 things, and then the last thing is uniquely determined. For like the alternating group, where it's an even permutation, it's constrained to being an even permutation, it turns out to be like n-2. But I think that's sort of the most I can say about it. If you have more questions about it, I can talk about it offline or in the roundtable.
Okay. So there is another question by Mehdi Mala. Can you say a bit more about the reduction from graph symmetry to general action of the symmetric group?
Again, I'm not sure how much I can say in the limited amount of time, but again, the intuition is just that the graph symmetry is the action of the symmetric group on pairs. So this is sort of what I tried to pictorially represent here. So here, if we have a permutation on 6 things, this basically, and here, okay, I guess if I have a small range function on 6 things, this induces a small range function on the edges of this graph. So for instance, if 3 maps to 2 and 5 maps to 6, then this edge between 3 and 5 maps to this pair 2, 6. And this is, again, this is essentially the only thing that is needed in the reduction.
Okay, thank you. So another maybe question, one of my questions. So you showed that when we have graph symmetries, then there cannot be a very huge gap between classical and quantum. Mm-hmm. But for other kind of symmetries, there may be some large gap. Mm-hmm. I think it's one. So how do you construct these large gaps? Do you reduce to some specific instance?
Right. Essentially, what we do is we show that you can basically take any permutation group and any problem with a query complexity speedup and turn it into a problem that is with a query complexity speedup that is also symmetric under that permutation group. Okay. So you can somehow just like add symmetries to any problem you like at the cost of some additional queries, and the cost turns out to be precisely this this B of G measure. I sort of mentioned how there is like a nice intuitive query complexity definition of this B of G, and that turns out to be precisely why we are able to construct speedups when B of G is small.
Okay, thank you. So I think it's almost time, so I would like to thank you again. And if you have more questions, maybe we can talk again later at the end of the session at the round table. Okay, thank you, William.
Thank you.